back. I decided to try something a bit different. I want to talk to you about some of my older projects. Projects that I built many years ago and that I still use to this day. So it's not projects that I built in an afternoon and then never opened again. It's projects that have been in use ever since they were built. And the one that I want to talk to you about today is this thing. This is my high voltage variable power supply. You may remember this from my Magic Eye vacuum tube video. I've used this to power the various tubes. So if you're curious about how this thing works, what's inside it, and what are some of the common problems associated with such a design, and many more things of course, then keep watching. So what is this thing? Well, first of all, it's a really heavy box. That's because there's a huge transformer in it from an old vacuum tube radio. And this is what is giving us our first two output voltages. I've got here a 6.3 volt AC, so this is a typical filament voltage for vacuum tubes. Then I've got a 220 volt AC output. This is basically the anode winding of the vacuum tube transformer. And then this is rectified in this 290 volt DC output voltage. And until here we've got simple rectifier. Now moving on to the variable part, we've got our variable DC voltage output, which is measured by voltmeter and the current by a milliammeter, and then the output voltage can be set using this knob. So if I turn this thing on, we can see that there's no current going through it, which is normal since there's nothing connected to the output load, and the output voltage can be set using this knob. So I can go down to 28 volts or up to a maximum of 270, and then anything in between. Now these two switches, one of them is to turn the output on or off, so we can simply disconnect the output. This is in case you don't want to physically unplug the wire, you just turn the switch. And then this other switch is here for some of the problems I had with it. So I'll get back to this a bit later. So how do you build a linear power supply? Well, before looking into my device, let's look at some other examples. This is what your basic supply looks like. The most basic supply. You're using your main supply voltage, can be 220 volts or 110 depending on the region of the globe you're in. You'll be using a transformer, some diodes to rectify the AC, and then a filtering capacitor. It doesn't get more simple than this. Now of course you can complicate things. The first thing you can do is add a transistor, like we have in this arrangement. Now in this case the output voltage, just like in our first example, is dependent on the turns ratio of the transformer, and the output voltage will be dependent on the current. So if you're using higher currents, then you will have a lower output voltage. But what this arrangement does is it multiplies the actual capacitance you're using. So this sort of arrangement is actually called the capacitance multiplier. You're using the transistor to amplify the filtering effect of the capacitor. But this is a fixed voltage supply that is not regulated. So how do we regulate this output? Well, not sure how well you can see it, but the next best thing you can do is add a Zener diode. This is a shunt regulator. In this case, the output voltage is no longer dependent on the transformer or the load, it's dependent on the voltage at which the Zener diode regulates. And this way your output voltage will be stabilized. It will have a fixed value that is not dependent on the transformer or the load. Now if you want higher currents, you can use a transistor to amplify this stabilization effect, like we see in this case. Here the voltage on the Zener diode is used to drive the transistor, and the transistor is driving our output. Now this is how we get a stabilized output voltage, but it's fixed. It's fixed to the voltage of your Zener diode. So how do we make it variable? Well, we turn the page. The next thing you can add to your supply is a potentiometer, like we see in this case. You are no longer supplying the transistor directly with the voltage that is on the Zener diode, but rather through this potentiometer, which works like a resistor divider. You're setting a voltage between the maximum voltage on your Zener diode and 0, and this is used to drive the transistor. therefore making your output variable. Now, you can complicate this design by using two transistors. This way you can use higher currents. And the next thing that is missing from our supply is a current limit. So all the supplies we've seen until this point will have a variable stabilized output voltage, but if you're drawing too much current from them, at one point they would self-destruct. There's no element in this supply to limit the current going through it. And that's where this transistor comes into place. So what we got here is a power supply that has a variable voltage output. It has a Zener diode for stabilization. It has a power transistor to regulate the output voltage. And it has this transistor to limit the current. Basically what we're doing here is measuring the current through this shunt resistor, and when this voltage is high enough, it will drive our transistor, which will turn off our regulating transistor. Now the current at which this transistor will act is set by this second potentiometer. So in this case we've got a power supply that has both a variable output voltage and a variable output current. Now all this sounds very nice, and the next best thing to do is to add proper reference voltages and proper comparators. And that can be done with integrated circuits. You can use integrated reference voltages, integrated operational amplifiers, or you can use both of these in the same package, like in the A723 integrated circuit that we've got in this schematic. This is a variable output voltage supply with an external transistor. Now this is a great supply, but it has one teeny little drawback. This IC will not work at high voltages. And that's the problem with most operational amplifiers or reference voltage ICs that you've got out there on the market. These ICs are not made for voltages exceeding 30, maximum 40 volts. Because if you want to work at higher voltages, you will need to make very large transistors and the silicon will be very expensive. So if you want to make a high voltage variable supply, you can't really go the integrated version. You need to design your supply from transistors. And this is the closest schematic I found that resembles what I've built. What we got here is a linear variable voltage power supply in which we've got a series transistor, we've got a reference voltage built with a Zener diode, a comparator built with two transistors, and the current limit built on a resistor that is placed on one of the supply lines. And basically this sort of supply was the inspiration for what I've built. So let's have a look at my actual supply, the one that we've got inside this box. So this is basically the schematic of the circuit I've used. Let's look at it quickly. So first of all, I've got my connection to the main supply, a fuse, capacitor, connections to the transformer, so the input winding, the high voltage output winding, and the low voltage filament winding. These go directly to some connectors from which it goes to the front panel. So I've got the AC output high voltage and then the 6.3 volt AC. Now this goes through a rectifying bridge and some filtration capacitors and turns into my high voltage DC unregulated output. Now the 6.3 volt AC I'm also rectifying using a second bridge, and this is just to get a DC voltage for LEDs or other supplies. In practice I'm using this to supply the multimeters. And this is the actual variable supply. I've got my input voltage on the left side and the output voltages on the right side. So I'm using a Zener diode reference. This voltage is then compared by the comparator to the voltage coming from this voltage divider on the output, where I also have this potentiometer. Now as regulating element I'm using an N-channel field effect transistor, and the comparator is directly driving this transistor. I've also got this Zener diode to limit the voltage between the gate and the source, so to protect the transistor from high voltages, and I've implemented this over current limiting circuit. So basically if the voltage over this 4.7 ohm resistor is too big, that will drive my transistor. This will happen roughly at around 100-150 milliamps. When this happens, the transistor will no longer let signal go into the field effect transistor, and the output current will be limited. Now, you may notice that there's a fifth transistor in this design. Basically what this is doing is turning my output, so the N-channel transistor, together with this fifth transistor, works like B-class output stage. Why is that important? Well, normally with a power supply you've got some huge capacitors on the output, and it's quite easy to charge them up. But once you're setting a lower voltage, these capacitors remain charged, and that's a problem. As you can see with the supply I've got right here, if I turn the voltage high, it will respond, but when I turn it low, it's slow to react. That is because the output capacitor is charged and there's no one there to discharge it. Now in my design, by adding this transistor, when the comparator is setting a lower voltage than you've got present on the output, this transistor will come into play and forcefully discharge the output capacitor through this resistor, so through R4. Therefore, as you can see in my supply, if I play around with the output potentiometer really fast, the output follows this motion. So there's no major delay on the output voltage. So enough chit chat, let's see how this thing looks on the inside. So let's start things off by taking the box apart. Basically, this is a standard plastic casing. You can get these without paying too much for them. And on the bottom side you can see the screws to this device. Basically there's four, well one is missing, 3 screws holding the box together, and we'll start by removing these. These are quite long screws since this has to go through the entire box. So I'll just put this here and let's see what's inside. So not much to look at. Got my power supply connector, the massive vacuum tube transformer, an old radiator from a processor, and the regulating transistor is placed on this thing, so this is used as a heat sink, and then the entire PCB is put here into this front opening. On the front side we can see the 2 multimeters, so one is the voltmeter, the other is the ammeter, and then all the connections to the various switches. Now to get a better look at this, I'm going to have to remove the PCB. So for that I'm going to have to turn it around again and look at these screws. So these 2 screws are here in place to hold in the radiator. The transformer is placed here on the rear side, so these 4 massive screws. But the front PCB is fixed in place with these 3 screws. So what I'm going to do next is remove these. Now the PCB is directly connected to the front panel, so when I pull one out, both of them are removed. So now we can see our main PCB. We got the 3 connections to the transistor, so this transistor is outside and these are not making that good contact, so might have some problems with that. I've got all the connections to the power supply, so the high voltage lines, the filament and everything, the big filtering capacitors, and then the other small transistors. And you can see it's quite a mess of wires here. So this is not something that I'm necessarily proud of, but hey, it works. Now one of the things I had problems with when building this was the ammeter. Problem is that on the board I have a large output capacitor, 47 or 100 microfarads. Now if I connect this thing to a load which also has a capacitor, then the capacitor will discharge into the output capacitor, giving me a very high current. Now the ammeter is designed for low currents, 100 milliamps, 200 milliamps. But when one capacitor is discharging into the other, you have a huge spike. And this is where this I-off switch comes from. This basically short circuits the milliamp meter so that when you're connecting a capacitive load, you don't blow out the milliamp meter. An interesting fact about this design is that you may see that this transformer is huge. I mean, this is a 300 watt transformer. And you can calculate that by measuring the core area. But if you measure the wires, so the wire thickness, the maximum power that you can actually take out of this is around 60 watts. So why is there such a big difference? I mean, this supply is designed with a current limit at around 100 milliamps, even though this transformer could supply much more power. Well, the thing is that this comes from a vacuum tube radio. And there are two output windings on this. So there's the filament winding and the high voltage anode winding. Normally, the filaments have a certain current rating and the anode circuit also has a certain current rating. But when you turn on the radio the first time, the filaments are cold. That means that the anode circuit is not using any sort of power. But the filaments, on the other hand, are using a very large amount of power since they're cold. So a typical current rating for a filament is, let's say, 1 amp. But that is when the filament is red hot glowing. When the filament is cold, the peak current can be as high as 3-4 amps, so much higher than the static rating. And that's why this transformer is so big. This needs to be able to handle the startup current for the filaments. But after everything has warmed up, it no longer needs to have such a high current rating, so the wires are kept thin. So did I have any problems with this device? Well, normally no. Everything went smoothly until one time when I broke it myself. Basically, when I built this thing, I only put a fuse on the input. I didn't put any fuses on the output. Now on the high voltage, I have a current limit in place, as you could see in the schematic. But on the filament side, there's absolutely no protection. So one time, my filament output short-circuited, and the only thing that managed to blow out was the trace on the PCB. So that's what this little wire is doing here. This is where the PCB burnt out completely and got interrupted. But other than that, I had no problems with this thing. It's simple and it's robust. And I hope to be using this for quite some time from now on. So, before closing everything up, there's one more experiment I want to perform, and that is to show how stable the output of this supply is. So what I got here is my output supply connected to an active load. So this is another project that I might cover at a different time. And then in series between the two devices is a milliamp meter and also a voltmeter. So if I turn on my output, without shocking myself of course, we can see that there's a small error in the voltmeter, but this can be fixed by calibration. Fortunately, I have a screwdriver lying around. There we go. Periodic calibrations of your equipment is essential. And now we see that we have 122 volts set. And my multimeter is somewhat good. And now if I change the load, so I go from 9 milliamps up to 20, 30 something, we see that the voltage is maintained. So there's no large variation in the output voltage. And at one point, if I increase the current enough, there will be a small drop in the output voltage, but this is just because of the comparator in this is built from discrete transistors. So it's not a proper operational amplifier. That may be a project for a different time. And if we increase the current enough, at around 100 milliamps, 100 something, so 130 in this case, we see that the current limit comes into play. So the output voltage abruptly drops. So this is the current limit in action. So why is the milliamp meter stopping at 111? Well, this panel meter was designed to show a maximum value of 999. Now, apparently it can go to 111, but that is already out of range. So anyway, this supply is a 100 milliamp supply, so we don't really care about higher currents. But we can see that the current limit is working and protecting the circuitry. So all in all, the supply works quite well, and is a very useful tool when working with vacuum tube circuits, Nixie tube circuits like Nixie clocks, Nixie bar graphs, and I've even used this when working on the rail power supplies, so supplies that you would normally power from the main supply, but use this thing as an isolating transformer, or directly supplying the switching supply with DC, but through proper voltmeter and milliamp meter. So, hope you like this sort of video, let me know in the comments. Hope you got some useful information out of this. Leave your thoughts in the comments. Thank you for watching. Make sure to subscribe to be up to date with all my latest videos. And see you next time. Bye bye.